Last time I took the guts from a hoverboard and used them to make a balancing bike. Each original hoverboard wheel is mounted on the bike and it drives the bike wheels with a drive belt. This makes the resulting velocity the same as it would have been when the hoverboard wheels were touching the ground, so now the balancing electronics still work as designed since the output velocity of the vehicle is still the same. I also split the bike in two so the back and front move independently, just like the two halves of the hoverboard. This means that I can turn the bike on the spot by pushing on the foot pegs. The bike wheels are omni wheels. They have small wheels around their circumference so that they can be driven in one axis by the drive belt, but they're passive in the other. In this video we're going to drive the bike forwards, and that's in the direction you'd expect the bike to travel on those omni wheels, and we'll see how that works out. But first I have a few other issues I want to resolve. It's actually really hard to drive the bike sideways and make it turn at the moment. Rotating the back and front of the bike in opposite directions is quite hard, and travelling sideways is even harder. When you ride a hoverboard you use your ankles quite a bit, so I'm going to upgrade my bike's steering system to make artificial ankles to tilt the original hoverboard electronics for me, rather than trying to lean the whole bike as much as I have to now. The plan is to tilt the hoverboard electronics with servos, but that means I need a clever steering wheel arrangement which is fly-by-wire and has two axes, so it's going to turn and move sideways as well. I 3D printed all the parts for the assembly, so just a quick ad from my 3D printing sponsor. Thanks to LolsBot for supporting my channel with 3D printers. It really helps having so many printers and making all the parts in parallel. And thanks to 3D Fuel for the filament for this project. All the parts are printed in Pro PLA+. So I've got some bicycle handlebars and I've mounted those on a metal tube so that we've got a steering stem. The column itself is made of multiple 3D printed parts. We've got bearings top and bottom here, and those two parts are fitted together so that we've got a plate there which holds them, and they're also glued together, so we've got that gap in the middle. My handlebar stem tube has a block on which is going to be glued on and screwed on with those holes, and that stem tube and the block fits in the gap on the main piece of the steering column with the tube going through those bearings. The bearings are bigger than the tube though, so I've made a 3D printed part which is also a clamp I can tighten up to shim that and make sure it fits nice and tightly. So there's the block installed on the gap, and you'll notice there's also a pulley on the top there, and again that pulley has a clamp on with a nut and a bolt done up, so that with the clamp on the bottom and the shim on the top, we end up with that tube fixed in properly. At each side of that block, attached to the main assembly, are two flap pieces, and those both hinge out so that block pushes them from the middle. Those are sprung together with a piece of bungee, and I can put more bungee on there or tighten it if I want it to be more springy, and basically that centres the whole thing, and because the flaps press against the orange part in the middle, it means it locks into the middle and doesn't float around. So I've got a potentiometer with the drive belt onto that big pulley, and that's going to allow me to measure the position in that axis. The pot pulley is smaller, so this is basically geared up, and that means I get much better resolution out of the analog ins on my Arduino I'm going to connect it to. At the bottom we've got another pulley, and that's to measure the other axis we mentioned, which is the side-to-side axis. So that fits onto some bearings in between two blocks, and then basically I've got plates go either side, and that holds the whole thing square. And that allows the side-to-side axis, but we still need to lock that in the middle. So again, there's two flaps which are sprung to the middle, and they press on that black part in the foreground, and that centres everything. So now we've got our two axes implemented. Of course we can turn this steering wheel like a normal bike, and we can also lean it sideways, which is going to make the bike go directly sideways. So that seems to be working okay. Everything centres in the middle so we can keep our zero position, but we do need to just put one more feedback pot on for that pulley at the bottom for the side-to-side axis, and then we need to put the twist grip on as well to make it go forwards, and then we can go and fit it back in the bike. So that's the last pot fitted in the bottom there, and again that's geared up so it turns much further than I'm actually leaning the joystick sideways. But that's just the controller. We still need to be able to tilt each side of the hoverboard to make it turn. There are two boards in the hoverboard and each one measures the angle and drives the wheels. So basically what we need to do is the equivalent of moving your ankles to tip the two sides in each direction. To do that, I've built this seesaw assembly. We're going to have two of these, and we're going to mount the two boards from the hoverboard on each of them. Now, there's a servo with a gear on there, so this is geared down this time because we don't need the full rotation of the servo, and I've got a tensioner so I can get the gear meshing just right. And we're going to use an Arduino Uno to read the analog pots on my joystick and drive those servos. It's pretty simple, we don't need much I/O, but I've put the Arduino in a pocket so it's really accessible and easy to get in and out, so that I can add other things to it like the twist grip to drive the jets, which are actually going to push this along later. So now when I turn the steering wheel sideways, each of those boards moves in opposite directions, and that's what we need, because that would be the same as moving your feet in opposite directions to make the hoverboard turn on the spot. If I move the handlebars sideways, then both of those seesaws move in the same direction, and that would be the same as going forward and back on the hoverboard, or in our case, going sideways. And all of these things mix together so that we get a nice motion there, and we can go sideways and turn if we want to, if that's even possible. Now there is some motion filtering, which is what the lag is, which probably needs tuning up. And if you want to know more about making robots move smoothly, then I did a video exactly on that, which I built this animatronic head and I'm controlling it again with an Arduino Uno, the cheapest servos I could find, and some analog pots. And essentially we've got a filter here which doesn't let the values change too quickly, so no matter what I do with the sticks we get this lovely smooth motion. I'll put a card in the video and you can check that out. So those are fitted in the bike and everything seems to be operating okay. So now it's time to give it a test.
But before we see how well that works, it's time for a quick ad from the video's sponsor, which is Qualcomm. Qualcomm have launched their robotics RB5 development kit, which is based on a Qualcomm QRB5165 SoC with machine learning inferencing capabilities. This means it's specifically designed for AI applications, including machine learning and machine vision. And Qualcomm have put together a new series of content, including videos and written documentation on getting up and running with the RB5 and a mounted camera. These videos are part of a new developer-first strategy for Qualcomm, and you may have seen this mentioned by Linda Van Doorn, SVP of Engineering at Qualcomm, in recent public presentations. The code is on GitHub and step-by-step instructions are detailed, so it's easy for AI and robotics engineers and embedded developers to learn how to develop AI features using the Qualcomm RB5 and ROS, the robotics operating system. The video series covers all parts of the development of a moving robot interacting with its environment using only its camera. If you want to find out more about the Qualcomm RB5 development kit, then check out the link in the video description. Right, let's get back and see if this bike can be controlled with its new controller and those servos.
So I fitted an actual motorbike saddle to this, so I'm actually slightly higher than I was before. This is going to take quite a bit of getting used to because there's no solid handlebars to hang on to. I feel like I need another handle for my other hand, but basically the steering wheel's floating around, so that makes it quite tricky to work out what's going on. So a bit more practice and I can in fact make it turn when I want to, and I can make it go sideways when I want to. I found that I have to lean and operate the artificial ankles to go sideways, and that's pretty much the same operation in a hoverboard. Turning on the spot's much easier though, because I can just turn the handlebars and it's pretty controllable. Although sometimes it feels like there's not quite enough power to support me and support the mass of the bike. And obviously the wheels are quite a lot of mass as well, which means there's a lot of rotary inertia on them. So actually stopping when I want it to is a bit difficult, and it feels like it overwhelms the power of the motors and the hoverboard drivers on the electronics. But it does take a bit of practice, the same as riding a hoverboard I guess. It's quite a weird experience balancing sideways like this and trying to balance and move these servos around to make the whole thing go where you want to. But there we are. I think probably that the whole thing's just a bit underpowered. The donor hoverboard I've used here is only rated at 240 watts, which I assume is for the whole thing. If we look at something like a one wheel, these are a couple of kilowatts, which is at least 10 times the power, and that might be for each wheel, so that's much more. I heard a rumour though that the hoverboard electronics will run up to 48 volts. The battery that comes with them says 37 volts, and I'm pretty confident that's 10 18650 cells, and it's only 2 amp hour. I was already running the whole thing on two 5S batteries, which are 5 amp hour, but I'm going to upgrade those to two 6S batteries and see if we can force some more power into those wheels. It might just destroy the electronics though, so first of all I've propped the whole thing up on a box. We're going to power it up and see what happens. But actually it seems to be running perfectly happily, immediately doesn't burst into flames at least. But I should probably sit on it and put some load on it and see what happens. Well, it immediately appears to be much more responsive than it was, so we are definitely getting some more power from that increased voltage. I still can do some things that seem a bit outlandish, and obviously we do have too much mass really, much more mass than the hoverboard electronics and motors that we're expecting, so if I do anything too crazy then we can still fall off it. But on the whole, with a bit of practice, if I don't do anything too crazy and I don't try and move in any direction too fast, if I'm much more controlled with it, still feels like I want to hang on, mind. But yeah, it seems like I can actually balance on this, and I think it's probably going to be okay to make normal curves and moves that you'd make on a normal bike, but with the whole thing being driven along. So a little bit more practice, but I think it's probably going to be okay like this. So yeah, the motors are getting quite warm because we're driving more power into them, and so are the electronic drivers on the boards. Ideally I'd have built my own balancing electronics like I have in the past, but I'm going to keep these here for now. The previous project where I did build my own balancing electronics and I used an O-drive motor driver to drive a brushless motor actually had one omni wheel on the front of a normal bicycle. So that bicycle could spin all the way round on its back wheel using the omni wheel on the front, but when you were bored with that you could ride it like a normal bike because of those little wheels on the front wheel. However, this bike still had pedals to make it go forward, and that isn't an option with two omni wheels, and I previously mentioned that we're going to use thrusters to drive it. Yep, it's some EDFs, which are actually pretty powerful. There's going to be one of these assemblies on each side of the bike. And yes, these are the same EDFs I used in the single caster jet skates video. They're pretty powerful and they push me along really easily, so check that out in my channel if you haven't already. So I've got two 100 amp ESCs because the EDFs are rated at 80 amps. Those are on the side where the thrust comes out and the battery's on the other side because that's where the wires are. But these things are pretty powerful. I fitted a twist grip onto the handlebars, and that's read by an analog in by the Arduino, which uses the Servo library to drive the ESCs. The whole thing's quite heavy though, so let's see if those EDFs push me as well as they did when they were on the caster skates.
Well, that's not quite as good as I thought it would be. I don't think testing in the house is a very good idea. I think maybe if we can launch it though and get it rolling, it might be alright.
The bike floats around quite a lot like I'm flying, so I really wanted to dress this up as a Star Wars speeder bike, but who knows what those are supposed to look like these days. I added some cosmetic details without wishing to add too much more mass to it, and also put the front flight surfaces on some poles sticking out the front with some conduit just for show, and it seems to still perform okay. I found this crash helmet that looks the part. It's made by a company called Hasbro, but now we need to launch it, so I got my good friend Matt Denton to give me a push to get going.
What happened?
That's pretty unstable. One go was okay, but then it wouldn't stop twisting and I couldn't straighten it, and then it just keeled over. And now with the jets sticking out, one's completely broken. So that's the end of testing for now. So the first run was okay until friction got the better of it and I ran out of power, but Matt pushed me harder on the second two runs and then it got really unstable. I'm pretty sure that's because the balancing electronics from the hoverboard aren't expecting the whole thing to go sideways. The inertial measurement unit that reads the angle consists of solid-state gyros and accelerometers for each of the three axes. All of this data would generally be fused together to give an accurate result. However, unexpected acceleration in one of the axes will probably cause some issues with the overall result. With hindsight, I'd probably been better off building my own electronics to make it balance like the previous bike, and I could have also tuned the response better and made it higher power. I really want to build another version though, and the plan for that is 4 mechanism wheels in line. Mechanism wheels are a bit like the Omni wheels, but the little wheels around the circumference are slanted at an angle. Normally these would go on the corners of a robot, but if we put all the wheels in line then we'd have the power of 4 motors to balance, and we could use a system of differential drive to drive mirrored pairs of wheels in opposite directions to kind of screw drive it along. So maybe more of that coming up in the future.